Hello everyone! In the previous video we made sure you had IRAF installed and ready to go, so now we can start with the actual Spectra reduction. First of all, I want to thank Professors Elena and Roberto Terlevich as well as Professor Ángeles Díaz for sponsoring this video by allowing me to use their observational data. The spectra I'm going to use are high quality recordings from the William Herschel Telescope. To complement the things I'm going to show you in these videos, I advise you to take a good look at the links within this video description. Indeed, the task configurations I'm going to use come from the third link. Finally, for those of you who, unlike me, do actually speak English, you will still find subtitles for this video, but now they must be manually activated within the closed captions menu of the YouTube video player. I have done it this way, so in the future I can add additional languages. Okay, that's all you needed to see me for. Thank you very much for all the comments, the subscriptions and the likes. Let's get started!
So, what are we doing today? In this diagram, which by the way you can find within this video description, we have a simplified diagram of the observational log from the data I am going to use in these tutorials. Each of these boxes represents the different sets of feed files produced by the telescope recordings. We have flat fields, sky flats, bias, and moreover, for each scientific recording, we have measured the flags from a calibration star and arc files to apply the corresponding wavelength calibration. Finally, in this observation, each object has its own flat field recording. On the right, we have a summary of the steps necessary to perform the bias, biassec, trimsec, flat field, and illumination corrections. Let's go over them. First of all, we need to combine all the bias files in order to generate a global bias feed file. With this file, we apply the bias correction to all our files. Actually, we shall apply the biassec and trimsec definitions at the same time with the CCDProc task. The third step consists in generating a global average flat fields file from all the flat field sets. This global flat, we need to normalize it. The following step consists in producing a global average sky flat file. This file needs a flat field correction, which we can do with the global normalized flat we produced before. We can continue then by generating an illumination flat with the illumination task. Now, since in this particular observation we have recorded flat fields for each scientific object, we're going to take advantage of this opportunity to produce a local flat field for each scientific object. We use flat combine to produce these local flats, and then we normalize them with the response task and the global flat field. The final step will consist in using the local normalized flat field and the global illumination file to correct the scientific images. Okay. Before taking each of these steps, however, since I am assuming this is the first time you use this task, we're going to check the configuration. Indeed, before reducing a set of data, the first thing you do is to make sure your tasks are properly configured for your work. For this task, I am using the setup described in the manual of Philip Massey, A User's Guide to CCD Reductions with IRAF. This is a good start for any data type, but in any case you should stick to your corresponding lab experience and preferences. The tasks we're going to use in this tutorial are Zero Combine, CCDProc, Image Combine, Flat Combine, Response, and Illumination. Here I have my IRAF terminal and an Ubuntu terminal to run DS9. This is the folder where I have my H2 Galaxies spectra in the form of feed files. Moreover, you can see over here several text files. These files are a list of my spectra organized by the frame name. For example, this file over here is the list of the bias frames for this observation. At the end of this video I shall give you some tips on how to generate this list, but for the time being you may wonder why I have included this one between square brackets. This has to do with my data form, so it may not apply to you. I'll be brief. Feed files consist in a series of images encapsulated within a single file with one header. In my case, every single file has only one image and one header. However, IRAF does not know that, so I need, for the time being, specify which frame I want it to use. Since I only have one frame and the counter starts at 1, I need to type 1 between square brackets. You will find that lists like this are effective to apply the single task to many files. For example, before going into step 1, check all these bias frames using this list to confirm they are uniform enough. For that, we're going to use the image statistics task. In this command line, there is only one parameter. The @ symbol tells IRAF that the input is in the form of a text file with the corresponding image names. These images must be in the same folder where we are executing the command. We press enter. This is going very slow for me, but don't worry, in your case it will be much faster. Here we can see that for every image, the number of pixels, the mean, the standard deviation in the pixel value, minimum and maximum values. From this table you can decide which bias deviate too much from the rest. For example, this first file has higher mean than the rest. Even worse than that, it has a lower number of pixels, which means that the image has a different size altogether. On the contrary, the third image has a much smaller mean for some reason. Since I have many frames, I can exclude these 3 images from the analysis and continue working. Let's do that. We open again our list of files, our list of bias files, and we erase the first 3 images. And we save it. Very nice. Okay. Now I can proceed with the first step on my list. We're going to combine all the bias frames to produce a global bias file. You might remember that for changing a task's flags, I can use the epar command followed by the name of a given task. In this case, 0 combine. Here we have it. The 0 combine task is used to average your bias files. In case you're wondering what are these frames I've been talking about, these images are used to account for the telescope's camera 0 level. In this analysis, we don't need dark frames, since in these professional telescopes the cooling reduces any dark current. Here we only need to modify a few values. The input and output names, better to set those with the command line. Here we have the combine flag, which sets the combining operation. You can opt between average and median. In my guide, it says median. Reject stands by the rejection operation. In my guide, it recommends to use creject. This method rejects only positive pixels according to the noise data from the CCD. Okay. And now, the CCD type flag. Let me try to explain this. If you put a valid type such as bias, flat, dark, IRAF will try to read this CCD type information from the header and only applies the current command line to the images belonging to these types. Myself, however, I do not have a valid CCD type on my headers, so I need to leave it blank. That should be all. Okay, to leave, we type 2 colons Q. Good. We are now ready to apply this correction. For that, we need to run this command. In this line, we see several flags. The first one, we already know it, it represents the input list of bias frames. Here we have the out flag, telling IRAF the name of the output file, while combine designs the averaging operation. We didn't really need to apply these as 2 flags in our command line since we already defined them as default values. Indeed, you will notice I really like long command lines in IRAF. However, I think it is easier to use this approach to play with the different task configuration, but you should always try the most natural way for you. We run it, and we wait. Okay, it's done. Let's take a look at it with DS9. We go to our Ubuntu terminal and we type here we have it. It looks good enough. Okay. Now, as we did before, we are going to use the imstat task to check it has similar values to the individual frames. Okay, it seems fine. Now, step 2. We need to remove from all our flames, scientific, flat, sky, all of them, this baseline from the CCD, which is accounted by the bias. This can be done with the CCDProc task. Let's take a look at it. As you can see, this task has really many parameters. This is because it can be done to apply all these initial corrections. Again, I find it easier to run it using command lines. First, we set CCD type again to none. If I did not say it before, you can do that. Type in space and enter. And now, let's just put all the corrections no as default. This is important because there are many tasks in IRAF which make use of the CCDProc task in the background, so they will try to use the default configuration. No. Okay, this is important as well. Here we need to set the orientation of the readout axis, in my case, as column. This is because my spectra, as you have seen, they are oriented vertically. Finally, we need to decide the fitting function. In my guide, it is advised to set it as legendary, which is the default value, but you can change it for the most suitable one for you. We leave. Now we are ready to apply the bias correction to our files. However, in order to decrease the number of steps, I want to define the bias section and the image section, or trimsec, simultaneously. These two corrections can be applied at the same time we remove the bias. By the way, you may be asking, what are these biassec and trimsec corrections? Well, in a few words, most current CCDs have one or even more regions not exposed to the incoming light. These regions in the CCD measure a base signal which should approach zero. These regions are known as overscan. This is somehow equivalent to a bias measurement performed with each observation. On the other hand, the trimsec correction is used to define where the scientific data is located in our CCD. By default, the trimsec is the CCD size minus the overscan region. Many telescopes write down the biassec and trimsec regions on the feeds header. Let's check this. For that, we are going to use the image header task. You can use this command line, where the long header flag has been activated to show the complete image header. Let's run it. Oops, you see, I forgot to type the frame number and I got an error. Let's try again. Now it works. Let's scroll up a bit. Here you have them. These are the default biassec and trimsec values from images. I should explain that in IRAF, square sections are defined this way. The former couple of values represent the first and last column pixel coordinates, while the later pair of values define the first and last row pixel coordinates. In most cases, these sections provided by the telescope should be fine. However, if you don't have them or you don't like them, you can check these coordinates from the images. Let's start by opening this image with DS9. A flat frame is necessary to check this. Here we have a flat frame. Seems nice enough at the edges, except maybe for these hot pixels on the right top corner, which start around, you can see there the coordinates, at 4098. Okay, so we cannot appreciate the overscan region from here. Let's open this image with IRAF. We close DS9. And now we're going to do that with the image plot task. Here we have it. Let's make this image bigger. In this window, we have a plot of the pixel intensity value along the line 2100. Actually, it means raw. Let's check the age values. we zoom over a region with the E key twice. The first one on the left corner, E, and the second one on the right top corner. Here we have it. Pixel measurements start around column 1, but it could take 5 safely. To set again the whole plot, again type twice A in the same location. Do the same E, E. The last measurement occurs at 966. We could use 960, save it. And now AA to go to the whole plot. And now, to see the values along column, we press C. Here we are. At the edge of this line, we can see the overscan region. Let's zoom over it. Here we have the overscan region, which starts around 4097 and ends at 4200. Okay. And now we zoom over here to the other edge, and the data starts measurement at pixel 1. Okay. Now to quit this window, remember Q. I hope you wrote down these values, for you need to compare them with the headers, biassec and trimsec definitions. Now that we have this information, we can actually apply the corrections. This is the command line I'll be using. Let's check its flags. As in the previous case, the first parameter corresponds to the list of input files. The list includes all the image types except the bias frames. The second parameter is the list of output files. IRAF will give you an error if the number of files is different, so no need to worry about that. Again, we don't have a CCD type in our headers, so no need to look for it. In general, to set a known value in IRAF, we just type quotation marks. Okay, this we have not seen yet. All these parameters are single value flags which tell CCDProc which corrections to apply. As you might have noticed, within the EPAR script, these flags could have a yes or no value. In the command line, in addition to these values, we can use the plus symbol for yes and the minus symbol for no. In this case, we're going to activate the overscan flag. This is equivalent to the biassec correction. And we're going to trim our image. This is the trimsec correction. Finally, we're going to apply a bias correction by activating the zero correction flag. Now, let's say we were happy with the overscan definition from the telescope. In that case, we type biassec equals image. We need to type trimsec equals our new coordinates, as I have done here. For the bias correction, we need to give the name of the image to use as 0 level for the CCD. This image must be in the same folder where we are running this command. Since we trust IRAF with this task, we don't need to see every step. Interact? No thanks. Let's run the command. It will take a while since I have many files. In the meantime, let me show you the input and output list I have used in this task. This is the input list. And this is the output list. On the first one, we have included the frame number so IRAF can recognize the images, while on the second one, we have the same file names but with a feeds extension. Taking these two steps, IRAF will recognize these files as single frames, and in the future, it will open them directly. That was all I wanted to show you. CCDProc has finished. Now we can continue by averaging the flat files. As you know, flat images are evenly illuminated CCD recordings, which are used to account for the difference in pixel sensibilities. Easy enough, we're going to use the flat combine task for this. Let's take a look at it. Here we have it. This time we leave the average as the combine operation, but we set again the rejection type as CC reject. Again, no CCD type. Of this list, you will find two parameters related to the CCD. These are the CCD red noise and the CCD gain. Here we have good and bad news. The good news is that IRAF can read the information in each frame header. The bad news is that you need to tell it the keyword it's using for this stored data. For example, in my frames from the William Herschel Telescope, the CCD readout noise appears in the header as red noise without the E, while the gain is described as gain. Good job, that should be all. To run this task, we're going to use this command line. I think I have explained all these parameters already, so let's run it. By the way, you know command line has finished its work when the symbol of IRAF terminal reappears. There you have it. Let's open it with DS9. It seems uniform enough. Very good. Now we're going to normalize it. For that, we need the response task. This task, along with the illumination task, have been designed to correct both the small and large scale variations caused by illumination and transmission effects. Let's start by taking a look at this response task. Sorry, you must go to the long slit package to use this task. Now, epar response. There you have it. The few things I need to change here are the fitting function, which it is also advised to set it as Legendre, and in the low and high rejection in sigma, my guide advises 3 and 3. Okay, that should be all. Now we're going to use this command line. In this line we have 3 parameters. The first one is the input frame, the third one is the output frame, while the second one is the image which will be used for the response. In most cases, it is the very input image. The fourth flag activates the user input, which will launch the eyes feed window. Let me run this command to show you what this means. Feed the normalization spectrum for flag interactively? Yes. Here we have our eyes feed window. In here, we need our fitting function to reproduce as much as possible the continuum from the flat field lamp. This must be done while avoiding negative effects such as dead pixels, hot pixels, or fringes, for example. In our case, the spectrum seems quite clean, so we are going to assume all the accidents are natural, and we can give it then a high order. To change the order of the fitting function, we type 2 colons O and the order we want to give it. In this case, for example, 50. Press enter, we press fit, and there you have it. If we are happy with this approach, we press Q, and we have produced or normalized spectra. Let's minimize this window, and let's take a look at this image. DS9. There you have it. It's normalized, and it seems quite clean. Very good. We are now at step 5. We need to combine all the sky flat frame, and we can do this with the combine task. I can use the default values of the combine task. In this command line, the first parameter is my sky flat images list, while the second one is the output frame name. In the rejection type, This time we chose average sigma clipping, while we set the scale and the weight as mode. Finally, the default output value, when there are no pixels, that is blank, we set it as 1. We run the command. Okay, let's check the image. Okay, it seems a flat, uniform enough. Very good. Okay, now we need to apply the flat correction to this image. But to do that, we can use again the CCDProc task. This is what you need. This time, only the flat correction flag has been activated, and we just need to specify the frame to be used in this correction, which in this case is the global normalized flat. Very well, we run it, and it's done. The final thing to do with the sky flat images is using the illumination task to produce the illumination flag. Let's take a look at its parameters. Let me try first to explain this task. One source of error in our spectra is having a different amount of light not along the slit but parallel to it in the spatial axis. We use sky flats for this correction since in most cases they are the most evenly illuminated recordings we can have. To do this, the illumination task divides our spectrum into several regions. These are the bins, which we leave as the default value of 5. Then, as we did in the response, you need to make sure that objects such as bad pixels, or in the particular case of sky flats, are not affecting the illumination. And finally, we leave, as we did before, the low and high rejection in sigma of the feed as 3 and 3. Okay, that should be it. Now we can run this command. Now it's going to ask us if we want to determine the illumination interactively for the sky flat. We say yes. Here we are again in the ice feed window. We can set the location of the bins. The only advice I can give you here is to make sure that none of the bin edges is located close or at an emission of or absorption feature. Let's delete the default bins using I, and now we can set the new bins using the S key. S, S, four, and 5. That's it. Now that we have done this, we can press Q. Now we return to our IRAF terminal, and it will ask us if we want to determine the illumination interactively for the sky flat at bin 1. We say yes. Here we are. At this point, we need to give higher order to this fitting function. You remember how to do that? Oh, let's try a lower number this time, 20. Enter, and F to fit. Very good. We're going to delete these points, and we can delete them with the key D. Let's delete this one as well. Press F. Now that looks better. Yeah, we can delete this one. This one. Maybe this one. Very good. Now, let's say we're happy there. We press Q, and now it will ask us to try at the second bin. We say yes. Now the fitting has improved. We delete again these points. Okay, we're happy with this. Let's try again. Bin number 3. Okay, now the situation has improved here. We delete this point. We can increase the order a bit. 30 feet. Okay, that's nice. Okay, good enough. Q. Now, bin number 4. Again. D. Okay, Q. And the final bin. Okay. D. Yeah, why not? Very good, very nice. We could increase the order a bit more, but should be fine. Q. We are done. We can minimize this window. And now let's take a look at this illumination flat. DS9. There you have it. As you can see, along the slit location line, the pixel intensity variation is around the third decimal order. This is what you should have. Very small variations in pixels intensity. Rather, these are large scale variations. Okay, we are happy with this illumination flat. Now we have all the pieces to complete our data treatment. Normally, you would use this illumination flat and the global normalized flat to treat all your data with the CCDProc task. Myself, since I have flat frames recorded during all the night, I'm going to try something not harder, just longer. I'm going to repeat the previous steps to produce local flat frames for each object. I already know how to do that. For example, let's say that these images are the flats corresponding to object 1. I can use the flat combine task to produce a local flat file. Press enter, and it's done. And I can do the same for object 2. And now I have the flat for the object 2. Now I need to normalize these flat files. For that, I'm going to use the local flat and normalize it with the global flat. And it will give me the normalized object 1 flat. And I press enter. Yes. This is the same as the previous step. I was happy with it. Okay. Q. And it's done. And now for the second object. Yes. Okay. Perfect. Q. Minimize. Perfect. And now, in the final step, we're going to use the CCDProc task to apply the flat and illumination correction. For that, we're going to use this command line. In this flag, as you can see, I have activated the flat correction and the illumination correction. And I have given the name of the object 1 flat and the illumination flat. Okay, we run it. That's it. With these 10 steps, you have completed the fundamental pixel intensity corrections in your data. Now you just need to repeat the steps, this final step in particular, for all your objects as well as your calibration stars. In the next video, we will be looking at technical correction of the CCD, which may have affected our frames. While on the following ones, we will be taking care of the physical corrections. But before saying goodbye, I promise you a few tricks on how to generate these lists. On many occasions, you will be working with data from someone else or from a telescope which has free access to the data you need. In that case, you most likely will have a log file, such as the one I have here from the William Herschel. For example, the approach I'm going to show you will consist in opening this file within a spreadsheet software. The one which is freely available and it can be used in, I believe, all operating systems is LibreOffice. So let's just open it. Grab and pull this file to the spreadsheet window. And now we can open it. Now, make sure that when you say separated by, all the options are deactivated. We're going to do that manually. Press OK. I need you to notice now all this information, it's written within the same column. That's not useful for us. We want each piece of data in a single column. So how are we going to do that? Well, first we are going to remove these lines. We don't need them. Delete rows. Let me check everything's okay. Okay. Now, we need to select this column and we go to data and text to columns. Here you have it. Let me move this down a bit. I know this separated by can be very tempting, but in most cases it doesn't work. You should work with fixed width. Very nice. And now to create these separators and move them to define columns. Okay, this seems nice. For some reason we cannot extend this window, so that's okay. Perfect. And now the final columns. We go up. No. Okay. Everything seems fine. So we press OK. There you have it. Now there is a problem here. I delete this line. And now we press twice at each column edge to adjust their width to the text width. The object is fine. The coordinates. The air mass. The instrument, very important. The exposition time. Slit. Prism. Okay, perfect. Now I need to sort this data. What you need to do is to select the columns you have, and again data, and this time sort. The first thing I want is to sort them by the instrument. This way I can have the data organized in blue and red terms. Then I want to organize them by the object. Oops. Not by the coordinate, by object. This way I will have flats images, bias images, sky flats, all together. And finally, by the run. Okay. And now all my rows are organized using these parameters. Very good. For example, let's say we wanted the blue bias frames. Now we select these columns with the images and we generate a new sheet. Oops. Copy and paste. Now, this is still useless for us, for in here we don't have any extension. So we type here the extension we wanted, fit, and you might remember how my file name started by R, so R. And now you can use the upper sound symbol to combine these strings. So this one, and very nice. And the same for all the columns. Very good. Now we copy a new sheet, paste special, and now here we just need the text. No formula, nor anything else. Okay. This is my list of bias frames. Now we save this. Okay, this will be my bias frame 1. I'm not fully aware of the IRAF limitations on text files. I just know that column separated values work with IRAF, so we select them. And now we save. Happy note, it will save just the active sheet, which is the one we want. Okay. Very good. Now, the second trick for working with a list I'm going to show you now makes use of a text editor. I'm going to use Emacs because it's the one I know the shortcuts, but I'm sure you can do this with any editor you like, so no worries. So let's open this list. There you have it. Let's say we want to add the frame number to this list. For that, you can use these shortcuts. Alt-Shift-5, and now we open Query Replace. We type .fit, enter. Query Replace with .fit 1 between square brackets, and we press enter. And now we need Shift 1. And it has changed all the fit extensions. That's what I wanted to show you. Please, if you have any doubt or you didn't understand some of the steps I took, please leave a comment. See you very soon.